So reciprocal identities are probably one of the easier identities. Right? Your reciprocal identity says if I have a sine of theta, that's going to be equal to 1 over cosecant theta. And cosine theta is going to be 1 over secant theta. And tan theta is going to be 1 over cotan theta. So these are kind of intuitive. And similarly, cosecant theta would be equal to 1 over sine theta. And secant theta would be equal to 1 over cosine theta. And cotan theta is equal to 1 over tan theta. Those are your 6 reciprocal identities. And like I said, they're kind of intuitive because sine goes to cosecant and cosine goes to secant and tan goes to cotan. And if we wanted to, prove this or show this, if I know, if we know SOHCAHTOA, right? If we're okay with that, let's see how I could do this. All right. And we know if I have a 30-degree angle, I know that sine of 30 degrees is equal to 1/2, right? My opposite over my hypotenuse. But cosecant, we know cosecant of theta is equal to my hypotenuse over my opposite. So if I was looking for the cosecant of this, I could say cosecant of theta is equal to 2 over 1. And what I could do is I could take the reciprocal of both sides of this equation, right? This is really like cosecant over 1. I could flip this, take the reciprocal of both sides, and I would find that 1 over cosecant of theta is equal to 1/2. Well, if sine of 30 degrees, or theta, sine of 30 degrees is 1/2, this should have been 30 degrees, and 1 over cosecant of 30 degrees is 1/2, right? Then sine of 30 degrees is equal to 1 over cosecant of 30 degrees. Sine of an angle is equal to 1 over cosecant of that angle. So these reciprocal identities are generally taught in college algebra and trig, and they're taught in college algebra and trig because when we start doing trigonometric functions and we're using our calculator, one of the main reasons is our calculator only has sine, cosine, and tangent. Right? Those are the only buttons on our calculator. So anytime we would have to do a calculation requiring the reciprocals, cosecant, secant, and cotangent, we would have to put it in the calculator as a reciprocal identity. So it was important in college algebra and trig to know this, because to do certain calculations using your calculator, you wouldn't be able to input it without reciprocal identities. So that's why it was included in the curriculum. So your cofunction identities, cofunction identity, we actually, in the last section, we ran across a cofunction identity, and it's when we talk about special triangles. But again, let's look at it using a 30, 60, 90. And a co-function identity shows that from one perspective, right, from this perspective, I'm standing over here, I know that sine of 30 degrees is equal to 1/2. But if I was standing up here, I'm wearing a dress, right? From here, from 60 degrees, I would say my adjacent over my hypotenuse, which is cosine of 60 degrees is equal to 1/2. Right? So my function values are the same. Therefore, cosine of 60 degrees is equal to sine of 30 degrees. Right? They're both equal to 1/2. But it's a different perspective. So from here, it's my opposite and my hypotenuse, but from here, it's my adjacent and my hypotenuse. Two different perspectives. So if I wanted to write that as a formula or as an identity, right, instead of writing 60 degrees and 30 degrees, I would have to use theta. So let's just say I wrote cosine of theta, theta looks funny, is equal to sine of what? What would I put in there? Right? I wouldn't put theta because it wouldn't be the same angle. I wouldn't say cosine of 30 is equal to sine of 30. That's not true. The cosine of, oh my goodness gracious. The cosine of 60, that's what I have here, good. The cosine of 60 is equal to the sine of what? It's the sine of 30, but how am I getting 30? Well, I know these two angles are complementary. They add up to 90. So I could write this as whatever theta is, this is going to be 90 degrees minus theta. Right? So if this is 60 degrees, this will be 90 minus 60, which is 30. Right? If this is 70 degrees, then this is going to be 90 minus 70 degrees, it's going to be 20. Your co-function identities are less intuitive than your reciprocal identities, right? Your reciprocal identities, well, personally, to me, they kind of made sense. These are a little tougher to memorize, but if you go in your textbook or your ebook, it's on page, I believe, 540. Well, it's in section 5.2, so you'll be able to see them all. But in this case, we'll just review them real quick. Sine goes to cosine, and cosine goes to sine. I like to look at it like this. You know, if I have to memorize something, I got to come up with a way to memorize it. And similarly, tan goes to cotan. So cotan goes to tan. And lastly, secant. Let's say I got a green pen. Secant goes to cosecant, and cosecant goes to secant. You can see those. So those are your co-function identity. In section 5.2, I'll show you why we use them. We do them when we're solving triangles, right triangles. We use them, and you won't even realize we're using them. So as this section continues, they ask us to use co-function identities to find equivalent values for these given trigonometric functions or trigonometric values. So for example, this one says sine of 19. So we want to use our co-function identity. I know sine goes to cosine, and it would be, 90 minus theta 90 minus theta. So in this case, theta is 19. So it would be cosine 90 degrees minus 19. So our final answer would be cosine 71 degrees. So that's what they want you to do. So if you want to take a minute and try the next two, and then I'll work on them. I'll give you a chance to write them down and try to work them out. So cosecant, I know, goes to secant, and it would be 90 minus theta. In this case, theta is 35 degrees. So I'm going to have 90 minus 35, which I believe is going to be secant 55 degrees. Now this one's interesting because we could do this one of two ways. Let's see. I know this is equal to cotan 90 minus pi over 7. So now you have I don't want to say a dilemma. We could do one of two things. We could, this is written in degree measure and this is written in radian measure. So we could either convert this to degrees or convert this to radians. Now, I don't know how comfortable you are, but in pre-calc, we should get used to radians. 90 degrees is pi over 2. So this would really be cotan pi over 2 minus pi over 7. Right? And then that's going to be cotan, what's pi over 2 minus pi over 7? Can you do that quickly? I know what it's going to be. It's going to be, my denominator is going to be 14, and I'm going to have 5 pi. It's going to be, this is my guess, 5 pi over 14. And how I did that is I multiply the denominators, and that's where my 14 came from. And then I cross multiply from the bottom up. So that would give me 7 pi minus 2 pi. So I'm going to have 5 pi over 14. Especially in pre-calc, this is the best way to add and subtract fractions quickly, right? So no matter what you do, you could just multiply your denominators and then cross multiply from the bottom up, and then whatever the operation is. So 7 pi minus 2 pi, that's where we got it from. Easy way to do addition, subtraction of fractions. Next in this section, they ask us to do some problems on the calculator. So on the calculator, they just want us to do an exercise finding a decimal approximation. It says use the calculator, find the decimal approximation to 4 decimal places, and then they say cosine of 21. So this is pretty easy. All you have to do is hit cosine and 21. There's no 21 button, so you have to use 2 and 1, and then hit enter. All right, that's the trick. Well, honestly, the only trick here is you have to make sure your calculator is in degree mode. Be sure calc is in degree mode. All right, how do I get my calculator in degree mode? Let me see, I think I have a calculator here. Just keep clicking away, there it is. So if I go, I put my calculator on, I go to mode. Right now it's in radians. I want to make sure it's in degree. I'll go over to degree and I hit enter. And then I want to quit out of this. So now I'm going to quit. I'm in degree mode. So I could do cosine 21, enter. And hopefully we all agree for decimal places, it looks like it's going to be 9336. That's what we're going to do. 9336. All right, close this now. Get rid of this. Exit. So my answer is 0.9336. So similarly, here we're going to do tan 52.6, enter. Pretty easy stuff. So we're going to get 1.3079, 1.3079. This one's a little trickier because it's a secant, and we don't have secant on our calculator. So we're going to have to rewrite this in terms of sine, cosine, and tangent. So secant is the reciprocal of cosine. So this would really be 1 over cosine 55. Right, so in my calculator, I'm going to have to do 1 divided by cosine 55. Enter. So let's see if I can get the calculator up and see if this works. So that's not what I want. So I might have to change my mode again. Yep. I should have turned it off. I'm in degree mode. I want to do 1 divided by cosine 55. These are my reciprocal identities. And hopefully we get 1.7434. 1.7434 approximately. And that's how we use a calculator to do these. So this section continues on, and now we want to do the inverse. They're giving us what the function value is equal to, and we want to find what theta is. So in order to do this on your calculator, we kind of talked about this before, right? We want to do the inverse function. So on our calculator, we want to do second cosine. And if you see above the cosine, you'll see cosine to the -1, right? And we talked about that being the inverse function. And then we could put in our 0.8771, enter. And hopefully, it says round to the nearest degree, and hopefully we get approximately 29 degrees. Show it on the calculator, sure. On the calculator, mode, degree, enter, and I want to do set, oops, I want to quit out of here. I want to do second cosine 0.8771. And it says round to the nearest degree. I got 28.7, which would round to 29 degrees. So hooray, I did it correctly. So for this next example, we're going to do the same thing. You're going to do second tan, and we're going to put in this 26.0307, and then hit enter. And we're going to get theta is approximately, we all agree, we get 88, I believe 88 degrees. So we can find the function value given the degrees, And we could also, when given the function value, we could find the degrees. All right, so we could work this both ways. If we're given the degrees, we could find the function value. When we're given the function value, we could find the degrees. So if you had to solve a right triangle, to solve a right triangle, if it asks you to solve, which it might not, but if it asks you to solve a right triangle, that means find all the missing parts. Find all missing sides and angles. You should be able to find everything. You're given enough information here where you should be able to find it all. So how would we go about doing this? Well, let's take a little inventory of what we have, right? We have the hypotenuse and we have one of these angles. If you want to call it B, C, right? So we want to take a little inventory of what we have. We have an angle and a side. So we're at the hypotenuse. So we want to think about TOA, right? Because we're going to have to work with other sides here. And ideally, we want to start by finding the easiest thing to find. So right away, the easiest thing to find here would be angle B, right? Angle B is 90 minus 34, right? Because these are complementary angles. So angle B is what, 56 degrees, right? 56 plus 34 gives me 90, yeah. So we find angle B, be the first thing we want to find. And we want to keep in mind, we want to find all the angles and all the sides. Right? And they gave us angle A is 34 degrees, and they gave us side C is 13, and angle C is 90. That was the information they gave us. We found that angle B is 56. So really, all we have to find is A and B now. I like to move alphabetically, just to be consistent. So I'm going to look for side A. So if I'm looking for side A and I'm given 34 degrees, I'm looking for this side and I'm given this side. So what trig function best fits? Well, it's my opposite, my hypotenuse. This looks like sine. I know sine of theta is equal to my opposite over my hypotenuse. Therefore, sine of 34 degrees is equal to A over 13. And now all I have to do is solve for A, get A by itself. So I multiply both sides by 13. So that's gone. So really I have 13 times sine 34 is equal to A. Right? So you could do that on your calculator. I believe A is approximately 7, we'll round to the 10th, 7.3 units. 7.3 units. So we found A. Now, if I wanted to find B, how would I find B? I'm going to pause it. So let's think about B here. How are we going to find B? Well, I know A is approximately 7.3, right? So there's two ways we could go about finding B. We could find B using Pythagorean theorem, right? We have two sides and we're missing one side. So I could do A squared plus B squared equals C squared. That would be one way of doing it. That would be a way I do not recommend doing it. I don't recommend using Pythagorean theorem at this point for two reasons. The first reason is I don't want to base an answer off an answer I derived. If I could avoid it, I don't want to use one of my answers. I could have made a mistake, and if I use it, I'm going to make 2 mistakes. So ideally, I don't want to use any values that I've derived. Secondly, even if I got this right at 7.3, this is an estimated value. So this is not the actual value. This is an estimate, right? These are exact values. Anything that's given to you in the textbook is an exact value. We got this, and we said A is approximately 7.3. So if I were to use Pythagorean theorem, I would be using an approximation to find a value that I'm going to approximate. So I'm getting further and further from the actual value. So that's why I don't recommend using Pythagorean theorem. As a last resort, I would use it, but in this case, I wouldn't use it. In order to find B, I would use my trig functions, right? I'm given 34 degrees, I'm given the hypotenuse, and I'm looking for the adjacent. Adjacent and hypotenuse, that's cosine, right? Cosine of theta is equal to my adjacent over my hypotenuse. So I could say cosine of 34 degrees is equal to B over 13. And then I could multiply both sides by 13. And just like before on my calculator, I'm going to do 13 cosine 34 is equal to B. And then I'm going to find the approximation. Right, if we work this out, it looks like B is approximately 10.8. That's what I get. So we solved the right triangle. We found all the missing sides, and we found all the missing angles.